AI uncovers 86,000 hidden earthquakes in Yellowstone. What does it mean? Imagine a hidden world of seismic activity, buzzing quietly beneath one of the most iconic landscapes on Earth. Yellowstone National Park, famous for its geysers and natural beauty, hides a secret that could reshape our understanding of volcanic systems. Using advanced artificial intelligence, scientists have uncovered an astonishing 86,000 previously undetected earthquakes beneath the park's surface. This groundbreaking discovery not only reveals swarms of seismic events, but also shines a light on the mysterious underworld of Yellowstone's volcanic system. And this is just the beginning of what makes this story so fascinating. Yellowstone, more than meets the eye. While millions of visitors flock to Yellowstone each year to marvel at Old Faithful and the park's otherworldly geothermal features, few realize the immense geological forces simmering below. Beneath its picturesque surface lies one of the most active volcanic systems on the planet. This system powers the park's geysers and hot springs, but also poses potential risks due to its volatile nature. Understanding this hidden world is critical, not just for Yellowstone, but for volcanic regions worldwide. A recent study published in Science Advances, July 18th, has taken a significant step forward in unraveling these mysteries. Led by Bingley, an engineering professor at Western University, alongside collaborators from the Universidad Industrial de Santander in Colombia and the U.S. Geological Survey, the research team employed machine learning techniques to analyze 15 years of seismic data from the Yellowstone caldera. Their findings? A staggering number of previously unnoticed earthquakes, roughly 10 times more than had been manually detected before. What exactly is a caldera? To fully grasp the significance of this discovery, it helps to understand what a caldera is. The Yellowstone caldera spans parts of Wyoming, Idaho, and Montana and is essentially a massive depression formed after a colossal volcanic eruption drained the magma chamber beneath. Unlike a volcanic crater, which forms from an explosive outward force, a caldera results from the ground collapsing inward after the magma chamber empties. This distinction is crucial because it highlights the structural instability of the region, making it a hotspot for seismic activity. With the aid of AI, researchers have now documented a total of 86,276 earthquakes in Yellowstone between 2008 and 2022. This vast dataset provides unprecedented insight into the park's seismic and volcanic behavior, offering scientists a clearer picture of how these processes interact over time. But here's where it gets controversial. Do these findings suggest that Yellowstone is becoming more seismically active, or are we simply getting better at detecting what was always there? The phenomenon of earthquake swarms. One of the most intriguing aspects of the study is the prevalence of earthquake swarms, clusters of small, interconnected quakes occurring within a confined area over a short period. These swarms differ from aftershocks, which are smaller tremors that follow a larger May shock. In Yellowstone, more than half of the recorded earthquakes were part of such swarms, indicating a unique pattern of seismicity. But why do these swarms occur? Researchers believe they may result from the movement of underground water and sudden bursts of fluid pressure along fault lines. Interestingly, the faults beneath Yellowstone are described as immature, meaning they are rougher and less developed compared to the smoother, more established faults found in places like Southern California. By analyzing these faults using fractal geometry, a mathematical approach that identifies self-similar patterns, the team gained new insights into their irregular structure and how it influences seismic activity. Fractal geometry, first introduced by mathematician Benoit Mandelbrot in 1980, allows scientists to quantify complexity in natural phenomena, from jagged coastlines to branching trees. In this case, it helped researchers characterize the roughness of the fault lines beneath Yellowstone, providing clues about why earthquake swarms behave differently here than in other regions. Implications beyond Yellowstone. The implications of this research extend far beyond the borders of the national park. According to Bingley, who specializes in fluid-induced earthquakes and rock mechanics, understanding seismic patterns like earthquake swarms can enhance public safety measures and inform communities about potential risks. Moreover, this knowledge could guide the development of geothermal energy projects in areas with high heat flow, ensuring they avoid dangerous fault zones. Before the advent of machine learning, detecting earthquakes relied heavily on human analysts painstakingly sifting through seismic waveforms. Not only was this method time-consuming and expensive, but it also missed many subtle events that AI can now identify with ease. As Lee pointed out, if we tried to analyze all this data manually, it would be impossible. It's simply not scalable. So, what does this mean for the future of seismology? With AI revolutionizing our ability to detect and interpret seismic activity, we're entering a new era of discovery. Yet, questions remain. Are immature faults more prone to generating earthquake swarms? Could these patterns signal impending volcanic unrest? And perhaps most importantly, how should we balance scientific curiosity with the need to protect vulnerable populations near active volcanoes? This study, titled Long-Term Dynamics of Earthquake Swarms in the Yellowstone Caldera, was authored by Manuel A. Flores, Bing Q. Lee, David R. Shelley, Mia V. Angulo, and Jose D. Sanabria Gomez. Published on July 18, 2025, in Science Advances, it invites readers to reflect on the delicate interplay between technology, science, and nature. DOI 10.1126/SciAD.ADV6484 https://doi.org/10.1126/SciADV.ADV6484. Don't miss out on the latest breakthroughs in science and technology. Subscribe to the SciTech Daily newsletter today. https://scitechdaily.com/newsletter. Machine learning uncovers 10 times more earthquakes in Yellowstone caldera. Beneath the surface of one of America's most beloved national parks, a hidden world of seismic activity has been quietly unfolding. Yellowstone National Park, a sprawling landscape of geysers and wildlife, is also home to one of Earth's most dynamic volcanic systems. But now, thanks to a groundbreaking study, we're seeing this subterranean world in unprecedented detail. Published in the prestigious journal Science Advances on July 18, the study led by Western engineering professor Bing Lee, in collaboration with researchers from the Universidad Industrial de Santander in Colombia and the United States Geological Survey, has turned machine learning into a seismic detective. By re-examining historical earthquake data from the Yellowstone caldera over a 15-year period, the team was able to uncover a seismic treasure trove, approximately 10 times more earthquakes than previously recorded. But what exactly is a caldera? Think of it as a massive bowl-shaped depression that forms when a volcano erupts and the magma chamber beneath it empties, causing the land above to collapse. Unlike a volcanic crater, which is formed by outward blasting, a caldera is the result of an inward collapse. The study's findings are based on a significantly improved dataset, which now contains 86,276 earthquakes spanning from 2008 to 2022. This dataset, collected with the help of machine learning, has greatly enhanced our understanding of the complex volcanic and seismic systems at play. One of the most intriguing discoveries is that over half of the earthquakes recorded in Yellowstone were part of earthquake swarms. These swarms are groups of small, interconnected earthquakes that spread and shift within a relatively small area over a short period. Unlike aftershocks, which follow a larger May shock, earthquake swarms are a unique phenomenon that can offer valuable insights into the underlying dynamics of the Yellowstone caldera. But here's where it gets controversial. While we can now detect and study these swarms more effectively, we still have much to learn about how one earthquake triggers another in a swarm. To a large extent, explains Lee, we can only indirectly measure the space and time between events. However, with our newfound dataset, we can apply statistical methods to quantify and discover new swarms, study them, and learn from them. As we continue to unravel the mysteries of Yellowstone's seismic activity, the potential applications are vast. By understanding patterns of seismicity, like earthquake swarms, we can improve safety measures, inform the public about potential risks, and even guide geothermal energy development away from danger, says Lee. The question remains, What other secrets does the Yellowstone caldera hold? What do you think? Share your thoughts in the comments below.